we also wanted to, maybe update people on what the survey said.
Yeah, I believe Martin is going to run through the relevant survey questions.
Okay.
And I think we can probably get started. We have quite a few people, and it is 11, and we know we have a lot to get through today. So welcome to session 2 of the age depth modeling of sedimentary deposits short course from GSA. I'm going to forego putting up the GSA RISE slide, but I will link to the GSA ethics, full ethics policy in the chat as soon as I'm done chitty chatting. And I'll also put in the links for the relevant things for today that you can be following along, that have the snippets of code and various things. So I'm going to turn it over to Martin, and he's going to, I think, start with some things that were in the feedback form, the survey. That thank you so much, everybody, for filling it out. So welcome, take it away, Martin.
All right. Welcome indeed. We've looked at the questions or the remarks that were put on the survey, and a few questions were about, or remarks were about, that I should perhaps slow down, especially at typing R commands. Others say I should speed up, but I think I'll go with slow down. So if I go too fast again, let me know, and I'll slow down. Then there were lots of questions about the cat. She's Amora, she's 7 years old, and she is, she is a character. And she's not very cuddly, but she's very much part of our family. She's from a rescue center. Also, one of the ideas was to perhaps pause every 20 minutes or so to see if there's any questions, and we'll try to do that. If you have any questions, as Amy was saying, you can pop them in the chat, raise your hand, or simply speak up. Yeah. And Amy has been very good in answering questions that were there last week, so I'm expecting that will continue to be done. And then there were a few specific questions that I would like to have a look at, perhaps. So I'm going to share my screen, hopefully. Yeah. Can you see my screen? Yeah.
Yes, we can. Yes, we can.
Good, good. Okay, so there were some issues with the commands that we were giving to plot radiocarbon dates and calibrate them. Yeah, so there was how you plot the distribution on the C14 BP on that axis, which axis correlates back to calendar years. How do we get a distribution plot from our data? Still trouble understanding the invisible axis during calibration, or how to read a calibration curve with the related probabilities. So I think these are all related. So perhaps we just go back a little bit to what the calibration curve looks like and how we get probabilities out of them, okay, out of the curve. So if we go back to R and we load the intcal code, so you type require and then open brackets intcal with capital I, capital C, and then close your bracket. That will load the intcal code, which has the calibration curves and also some calibration functions. Yeah. So if I want to have a look at the main calibration curve, the intcal 20 terrestrial calibration curve, then I can call it. I can simply say I can make a new variable, which in this case will be CC, calibration curve, and I assign to that the function. I call the function C curve, calibration curve, open bracket, close bracket, click. Yeah, so now I have this variable CC, which contains all the data of the calibration curve, of the curve itself. And this is sort of an array or a matrix with 3 columns and 9,501 rows. Yeah? So I can ask n row CC, how many rows are there in CC? 9,501. And the amount of columns and col CC, that's 3. Yeah. And so we can now have a look at, for example, if you just want to see what this whole curve, all the data looks like, we can type CC. And then we get a whole lot of numbers, but there's so many that we can really actually not see them well. Yeah, of course, there's 9,501 rows. So one thing you can do to just look at a part of the data is to use the function head, which just shows you the first 5 entries, the first 5 rows of the calibration curve. Yeah. Now we see again that these are 3 columns. The first column is years CalBP. So these are the calendar years, the known calendar years. And then the second column is the radiocarbon year of the IntCal curve belonging to that calendar year. Yeah. And then we've got the final column, which is the uncertainty of that radiocarbon year for that calendar year. Yeah. So do you remember that we used this function dnorm, so the normal distribution? For example, if we have a mean of 130 and an error, lab error of 20, for example, and we want to know what the likelihood or the probability is of a value, for example, 130, then we get a number, yeah? We get a certain probability. So with a mean of 130 and an error of 20 and assuming a normal distribution, if we then ask what's the probability of the value, the actual value being 130, that's around, well, 1.9%. And if we ask for another number, for example, 100, and it's less than, yeah, so it's a lower number. We can also ask that question for many values of dnorm. For example, if we have a value x, which becomes 1 all the way up to 500. Yeah, so we have x, which starts at 1, then 2, 3, 4, 5, 6, all the way to 500. Then we can ask to give us the dnorm, so the normal distribution probabilities for each of those values for x. And that gives us then a whole load of numbers. Yeah. Not very interesting, but we can then plot x against that value dnorm of x with 130 plus or minus 20, and that gives us then a normal distribution. Yeah. Now there was a whole lot of explanation for just saying that this dnorm gives us the probability of a certain value given the date, given the mean and the error that was measured. Yeah, is that okay? Okay, so the next step is then that we have our calibration curve. Yes, so I go back to my calibration curve, head CC, and I've got for each calendar year 0 CalBP, 1 CalBP, 2 CalBP, etc. the corresponding radiocarbon years. Yeah. Now, if I want to know for each calendar year what the normal distribution is for the radiocarbon year belonging to that calendar year, given the radiocarbon date, then I can ask for dnorm. The second column, because the second column of the CC is the radiocarbon years, dnorm, and I give the radiocarbon year, the uncalibrated date. That's not correct. So I ask, okay, give me all the probabilities, assuming a normal distribution, for all the values of the radiocarbon year for each calendar year of the calibration curve. And again, I get a lot of numbers. Now I can give that another name. Yeah, so I call it a variable mu or whatever. Yeah. And now I can plot the first row, the first column of the calibration curve, and then mu. And that doesn't show anything because we've got like these like 55,000 years. So we can then plot anything between 0 and 500 cal BP. And that doesn't look like anything either because it's all dots. So we can then write it, plot it as a line. And there we get our calibrated distribution. Yeah. So we're pushing our radiocarbon date through the calibration curve. So for each calendar year, we're asking how likely is my radiocarbon date given the int-cal radiocarbon age of that calendar year. Yeah. Now, luckily enough, we don't have to go through this whole process of getting variables and plotting them, because we can also simply use an existing function, calibrate 130 plus or minus 20. And that already gives us this calibrated distribution. Okay. Now, the next question has to do with this invisible axis. Yeah. So we've got quite a complicated graph here. So on the vertical scale, the main vertical scale has radiocarbon years. And it's this green curve which shows the radiocarbon years, the calibration curve. Horizontal scale, the main scale, is calendar years, years before AD 1950. And then we've got these weird gray distributions, and they're plotted. So for the radiocarbon distribution is this one, the bell-shaped distribution, which has the radiocarbon years here, and then an additional axis, which we don't really plot, which shows the probability distribution. Yeah. So we shouldn't interpret the heights of this distribution as cal BP. We should consider it as some sort of value which isn't really of relevance to us. We're only looking at the entire shape. And the same for our calendar year distribution, which is plotted on an invisible additional axis, which shouldn't be interpreted on the radiocarbon scale. Yeah, does that make sense? I hope. Any further questions related to that? No? Okay, there was another question about which calibration curve do you use if you're working in a lake? A very good question. So if you have a lake where you have an age offset of around 500 years or 1,000 years or 200 years, you would still use the terrestrial calibration curve, but you would adapt your ages. You would add a reservoir effect to your ages to take account of any age offsets. So don't use the int-cal, or don't use the marine curve for that, because the marine curve has gone through a whole marine model which takes into account, say, smoothing effects, and the same smoothing effects wouldn't apply necessarily to your lake. So you would use the int-cal calibration curve, but then add to, we'll see later how you enter such data, but you would enter your radiocarbon dates and also then any additional local or reservoir age for that lake, including its uncertainty. Okay.
And Martin, I had one more question that just came in the chat. Sorry, I could have waited, but the question, is it normal for RStudio to cut off the values? This is what I get when I type in dnorm cc2 130, 20. It says reached get option, max print. You can probably read this yourself. Omitted 8,501 lines.
Yes. So if you plot lots of lines, it will. I will tell you like that's just too many values to actually put on the terminal, so it just cuts them off. That's not really a problem. It's just that if you have a million values, it will not plot all the million, print all the million values on the terminal. So normally, if you have your calibration curve, in this case, it will plot 9,500 values. But if it's quite difficult to scroll through all of them. So if you just want to just look at some values, you can use head CC, as you said before, or the very opposite, tail, which shows you the 5 or 6 lowermost, bottommost values. Okay, so I wouldn't worry about that message. It's okay. Okay,
And Martin,
then
there's one.
Yeah.
Yep. Sorry, we should
No
figure
worries.
this out. Quick question about if there is time, and maybe this fits into somewhere that you already have planned, but can you quickly cover when it is appropriate to
11:30, right?
smooth the calibration curve before calibrating?
I myself never smooth the calibration curve. There are some software that allows for that. For example, Calib allows for that. If you, for example, have a sample which you know has accumulated over, say, 100 years, you can smooth your curve related to that. With Bacon or anything, we don't really do that. I don't think it affects things too much. Yeah, so if you think it has an impact, you could. I'm not sure if it can be done on Oxcal actually. But normally, I don't think in the end it does. I don't think it has much of an impact. Because we're just using. Yeah, no, I don't think it matters too much. But if you are worried about it, you could make your own calibration curve. So you could make a curve which is smoother than IntCal, and then use it as a tailor-made calibration curve and calibrate your data with that, or even use that in age modeling software. But that would also require quite a bit of explanation. I'm not so sure if that's worth it, but it might be for your case study, it might be worth it. Okay. Then there's also error multipliers for dates. We didn't really talk about that, but many labs will report a date, but also will have, whenever labs come up with the size of the error, the lab error, it's a bit of, it's not dark magic, it's a bit of an educated guess based on the age. So older samples will have larger ages, simply say larger absolute errors, but it also has to do with the whole run of the machine at that time, at that day when the samples were measured. How stable was the machine? What were the backgrounds like? What were the standards like? And based on that, the error, the reported error will be adapted a bit. And also some material will have larger lab errors than other material. So charcoal, bones, sediment, each type of date will sometimes get its own lab error multiplier, and it will be specific to a lab and specific to the machine and to the sample material. Okay. Yeah. Then there was also a question about the difference between different calibration software, or rather age modeling softwares. We'll be looking at that actually a little bit today, not in too much detail, but we'll be looking at today. Another question was, what format does our data have to be in? And also that will be covered today and next week. And there was also a question about an example of using R to analyze data, and we'll actually be doing that later today. Yeah. Okay. So that was us for now with the questions. And let's get started now. I hope you can see my screen here. So we'll be looking at a tiny little bit at classical or frequentist age models, and then spend more time on Bayesian age models because I like them more. We'll look at probabilities, what I mean, and how we actually go about this combining prior information with new data. It sounds quite esoteric, but it's that's how how do we actually go about that? Yeah. So when we decide on what age model to apply, or what there's lots of decisions involved, yeah, especially if you use classical age step models. For example, if we assume that we have a site here, a core on the vertical scale here, we've got the centimeters from 0 to 800 centimeters depth. So we've got 8 meters core, and here's the calendar scale, and we've got 9 dates or so, and also the surface, assuming it's a recent surface. Now, one thing that would generally be done first is to simply connect the different data depths with a straight line between each neighboring data depths. So linear interpolation between the data levels or the data depths, or short linear interpolation. And that used to be by far the most common model. I don't know if what you think of this model, but it's actually quite a strange and difficult to defend model actually, because it assumes that our accumulation rates were exactly constant between dated levels and changed exactly at the point where our material was dated. And so we were extremely lucky that we dated exactly there where we found this change in accumulation rate, but that's actually part of the model. Yeah. If you want to play along during the presentation, you can open your R terminal or R code, and you can type require clam to load the clam code, which hopefully you've already installed. And then you just simply type clam, and that is then running clam with all the default settings. It might, if you run this for the first time, it might ask you if it's okay to place a folder and you just say yes or type yes. Okay. I hope you can then also see that an output like this appears. And we'll look a little bit in more detail during the practical. But this is, say, the default age model. All right. But then it has a bit of a problem here in that there's a very abrupt change from very slow accumulation to suddenly very fast. And that might be a bit questionable. Yeah. Is such an elbow, such a sharp change, is that actually realistic for such a site? Perhaps not. So you might decide then to kick out one of the dates as outlier, because outliers and scatter does happen. Yeah. Then your model is a bit more smooth, perhaps looks a bit more realistic. Note that the lowermost dated level is around 700 centimeters depth, or 680. And beyond that, I'm simply just extrapolating my straight line until infinity. Yeah. So that's a very, very dangerous thing to do, but it can be done. And we then get an age estimate for 800 centimeters depth, around 22,000 years old. Very, very dangerous. So please don't try this at home. Well, if you're at home, you can do that. You can also assume something else having happened, and that's, for example, there might have been a hiatus. So where the site has been accumulating, and then there's a gap. Perhaps the lake lowered, the water level lowered, and there was no accumulation of sediment, or it was accumulating and then that was then taken away by some event, and then afterwards the lake starts accumulating again. Yeah, you can do that by typing clam hiatus equals 470. Okay. So that looks quite nice, I think. But if we do that, then we can also assume other things. We can say, oh, perhaps things were accumulating straight, entirely straight below the hiatus and entirely straight after the hiatus. If we think that's a reasonable thing to assume, then we can also do that. Then we type clam, comma, 2, and that's the age model type 2. The default is 1, which is linear interpolation. And then we've got 2 as linear regression. And we can then also say, oh, outliers equals 6. We don't do that here. Sorry, that's a mistake. Or we can also then get a second degree polynomial regression. So we've got the polynomial regression, which is option 2, but then with a second degree. So we have 2 as the third option. So 2, comma 2, comma 2. And we also invoke a hiatus. Yeah. Or a third degree polynomial regression. Why not? Well, there might be many reasons why not, because it becomes very quickly very unpredictable. Yeah, if you add more factors, more degrees to your polynomial function, it will start doing extremely weird things, especially at the ends. So then it quickly becomes very, very weird. Okay. Or you can use a smooth spline. That's the fourth option, the fourth type of age model. And generally that perhaps plots something that looks a bit more natural than exactly straight sections. Yeah. It's a tiny issue here, though, that there is this weird Back to the Future effect. Yeah, there's an age reversal. And it's not really steered by the data in any way. It is just going through this date and then going back through the other date. And that, of course, we hope cannot happen in real life in our sites, because we can quite safely assume that our site has accumulated in a monotonous way over time, without age reversals. If you do have a site with age reversals, then of course it can happen, but then yeah, you have to try other models. Okay. So yeah, being out of chronological order for a site it's a thing that does not really generally happen, we hope. And yeah, so we generally assume that our particles are laid down in order. Yeah, just like a stack of books. The books themselves might be published in different years and not in that might not be stacked in the way they were published, but yeah, the ordering as the layers of sediment are put down is hopefully increasing with time, right? Okay, so what we then can do to avoid these age reversals, we can then decide again to reject one of the dates. So we use the smooth spline, comma 4, but then we add as an additional option that one of our dates is outlying, the date number 6 from the top level. Or again, invoke a hiatus instead. Yeah. So, and each of these decisions will have large impacts on the ages of especially depths around the possible hiatus. Yeah. So huge impacts of your decisions on the ages, and the errors, the uncertainties of the models don't really reflect that type of uncertainty. Yeah, so there's this large additional unquantified uncertainty of whether the choice you made of model is the correct one. Yeah. So in many cases, we'll see that later, classical HDF models have actually quite underestimated the uncertainty by quite a large degree. So they're not really that useful. So if you want to to plot these types of age models, produce these types of age models, then here's the code again. Yeah, we require clam, and then you can, yeah, simply plot this code or write the code in the terminal, and you'll get the different outputs. Yeah. Just so we're all aware of it, we also have the website, yeah, the GSA age modeling course, which has for the sessions with all the or most of the commands that were given can also be seen back here, so you can follow afterwards what happened. And now we're in session 2A, and we've gone, well, we're around here now. Okay, so you can follow what has happened also after the fact. Yeah. Okay. Good. Now, what is this? Can anyone see what this is? And if you can, please speak out.
Santa Claus
Aha.
with someone on their lap, his lap.
Oh, very good. Have you got a good screen?
No, this is a laptop and I got my bifocals on.
Okay, because usually people say Santa, but they don't see that additional feature of the photo. And that is actually, this is Santa with a child on his lap. And this is made by an artist who has lots of different photos of the same approach of going to Google and then asking for Santa with a child on his lap. And then he downloads 100 photos of that. And then for each pixel, calculates the average color. And then we end up with not a clear picture, but like a fuzzy, uncertain, vague picture of where we can still get some information from. Yeah, in many cases, people will see Santa clearly, but sometimes in the model, the child, or often the child, will actually not be spotted. Yeah. And what's underlying is then 100 realities, 100 real cases of Santa with a child on his lap. All right. And that's what we're doing. We're creating in our computers lots of hopefully realistic simulations of what could have happened. And we put them then all together. So thousands or millions of iterations of likely scenarios put together. And that will then give us in the end, not a sharp image, but an uncertain image. And we want this uncertainty because we want to quantify the uncertainty, visualize it, and not neglect it, as is often still done in papers. Okay. Right. So one approach of doing that is by simply sampling many times. Yeah. So we take a random number from our dates, and then we do that for each date, and then we draw a curve through those randomly sampled ages. Yeah. And we repeat that process. And that's what computers are really good at repeating things in a dumb way, just simply repeating. Yeah. So the likelihood of an age being sampled is proportional to how high the calibrated distribution is at that calendar age. Yeah. So more likely calendar ages are more likely to be sampled. And then we simply draw curves through those sampled ages. Yeah. Do that then thousands of times. So that will then give us age estimates for any dated level, but also of undated levels. Yeah. Of course, for example, at 100 centimeters depth, we have no dated depth. Yeah, there's no date, but all those age models go through that depth anyway. So we can ask the age model, give us for all your 1,000 iterations, give us those 1,000 age estimate, point age estimates for 100 centimeters depth. And you can then plot that, and that then gives you an estimate of the age at 100 centimeters depth and its uncertainty. Yeah. Okay. Good. Now, the model here that we used here was simply a smooth spline or something. Yeah. Let's look a little bit more at the type of model we draw. So in this case, what we're using is we've got two calibrated dates, and we use this approach of sampling randomly ages from those dates, and where more likely ages are more likely to be sampled. And then each time we draw a straight line between the dates. Yeah. Then we end up with a very nice, very precise, very clear model. Yeah. But the weird thing is that the uncertainty is quite large around the dated levels, but the further away we go from the dated levels, the more certain our model becomes. Yeah. So the farther away you are from a date, the more certain you are of the age, which makes absolutely no sense. Yeah. And that's because the straight line, that's the feature that's just built in this model, that, yeah, the further away you are from dating information, the more supposedly you know. Yeah? So in effect, the fewer dates you will have, the more you will know, but it makes absolutely no sense. Yeah. So we should really throw away this type of straight lines as a stat model, because it just, yeah, it's too certain of itself. Yeah. Instead, we should be looking for models which don't accumulate linearly between one date to the next, but have some degree of freedom to find its own way. Yeah. And there, the further away you are from data levels, the more uncertain we are. And that is what we should be looking for in a model, I hope. Yeah. And that's the type of models that Bacon, Bicron, and Oxcal do. These are Bayesian models, which don't just throw straight lines between dates, but through some random processes, take steps between one date to the next. And if there's fewer dates, those steps will be diverging more than if there's more dates. Yeah, if there's more dates, that will be neatly together, because there's lots of information to choose the model. But if there's little dating information, there will be more divergence and more uncertainty, and which is exactly what we should be wanting. Okay. Right.
Martin, would this be a good time to pause and ask for questions on this recent stuff? Because I think you've covered a lot of really, really important things in the last 10 minutes or so. Questions, okay. People can raise hands or just speak out.
Any questions in the chat?
Oh, David, go ahead.
Yeah, I just have a question on this video right here. How does the model know how far to, in that area where you don't have any dates, how does it know how far to extend? Why couldn't it be twice that, in other words?
Oh yeah, here I just simply used 100 nodes or so, and it can lose itself. Yeah, so it doesn't really know that if it's going this way, that it should go back to the date. Yeah, this is just, yeah, it's just chosen randomly. So the process, we'll come to that, but the process of choosing models isn't entirely, there should be a process somehow where the model learns from the data. Yeah. So there's this MCMC, Monte Carlo Markov chain, or Markov chain Monte Carlo process, where over time the models will learn and adapt themselves better and better to the data, and we'll be looking at that. And in that way, in the end, you will see that models will do this and then return back to the data because they've learned about where they should be going. Yeah. I hope that answered the question.
Yeah, I mean, is it something that you can input into the model? How much freedom to give it, I guess? Or is it something
yeah.
kind of,
Yeah, for example, in Oxcal, you can change the K parameter value, which is the size of the steps. And if you set your steps very small, then you have many steps, and your model will be quite smooth. If you set large steps, it will be quite elbowy. And yeah, similar with Bacon, and not so much with Bcron, because Bcron has settings which you cannot change, which the user cannot fiddle with, but with Bacon and with Oxcal you can. And you're certainly invited to play with that, to see how different settings affect your model output. Yeah. How robust is your model to different types of settings?
yeah. Okay, thank you.
Cheers. Any other questions?
Yeah, two more questions. One asking, those are the iterations generated by Monte Carlo simulations? Question mark.
Yeah. They're not Markov chain Monte Carlo, they're simply Monte Carlo. So they're independent iterations, yeah.
Got it. And one of the fundamental questions of everything, how many samples do you need for age depth modeling, ideally?
How much money do you have? It really depends on your question. If you want to know whether the Younger Dryas event, or whenever your site happened at your event in your site happened at the start of the Younger Dryas within 10 years, then you need to get a lot of dates and a very robust and precise age model to get like 10 years precision. But if you want to know if your event was mid-Holocene, you might not even need dates, because you can already see from the other information you have from other dated sites in the region that whatever you're seeing in your core is more or less mid-Holocene. Yeah, so it depends a lot on the research question. That's one answer. And then as a member of the radiocarbon lab, you, of course, the more dates, the better. Yeah. There's also an issue. Sometimes the more dates, the more problems you uncover. And that's really, that can really be a big problem. I'm involved in several projects where we had a bit more money than usual, started to date more samples, and then you uncover a whole, box of Pandora, because there can be all kinds of issues that you simply don't learn if you just stick to very few dates. Yeah. But we'll come to that question later of how many dates we need.
And I also linked your double the dates and go for Bayes paper.
Yeah.
Which addresses that in part.
Yeah. So if the question is how many dates do you need double the amount that you have. So okay. So that brings us then to sorry.
Nope, great answer. Okay, so we'll try to pause in another half hour or something like that. Or do you want to? Will we be pausing at the top of the hour for a quick break? And then we could maybe answer questions after we get back from the break or something.
Yeah, that sounds
okay.
Good
So feel free to put them in the chat or hold them.
Okay.
Thanks.
Now, so one thing that I like doing a lot is looking at how what the community is doing and how so different things come into fashion and then run out of fashion. And for example, if we look at citations per year to different types of software, that's these graphs. I think it's quite interesting. So for Scholar Google, you can ask how many citations were there in 2005 to a certain paper. Yeah. Now, if you just focus on the left graph here, that just looks at generic calibration software. So there's Calib, which was written by Paula Reimer in the late 1980s. And that was actually one of the first software pieces that people could download or get on a diskette and then run to get calibrated dates. Yeah, so this is really the start of calibration, more or less. That became quite popular around the year 2000, around 400 citations or so per per year. And since then, since around 2010, it has become a bit less popular. And what has instead taken over, which since coming out in 1994 or so, is Oxcal. Oxcal is an online software made in Oxford. Originally, it was just meant for their own lab to just calibrate dates and make sense of the dates, but it has turned into like a really very widely used piece of software where most people will go to calibrate their dates, but also to produce more age models. And for example, if you have some ordered dates over a site where you know that some dates are older than other dates. Yeah. So that's the blue bars here. So they've really taken over, and many people will simply use Oxcal to calibrate their dates and report that in papers, and then also use that for their age models. Now it happens to be that Oxcal is Bayesian, and we'll come back to what Bayesian is, but it seems that has won over the more classical one. Why this took place? That's a question, and I don't know. Perhaps it's because it's from Oxford and it worked well, and it was people started using it, and therefore more people started using it. Because at the same time, there's also BCal, which has been around more or less the same amount of years as Oxcal, but is far less popular than Oxcal. Yeah. So yeah, there's a difference in popularity. Perhaps because Oxcal can do many more things than BCal. Now, if you look at age depth modeling only, so only at papers that produce approaches to age depth modeling, then a similar thing happened. So we've got in red papers that I'm aware of that propose and produce new approaches to age depth modeling. For example, we've got a mixed effect that came out in 2003 or no, 2004 or 5. Free shape, which was a model which actually never became available but for other people to use, only within one lab. And then CLAM, which I produced in 2010 as an R package. And then COPRA is a more recent one, which is mostly used for speediotherms in the speediotherm community. So what I can see is that since 2005, there's been quite a large increase to around 200 or so citations per year. And then since 2015, that's more or less plateaued out. And again, what we then see is that other types of age models have taken over. And in this case, again, it's the Bayesian age models that have become far more popular than the classical ones. Yeah. So in blue, we've got the P sequence, which is a specific model that is offered by Oxcal. And that's based on a paper by Christopher Bungramsey, where he describes that model, which we'll come back to later. And there's BCron, which is written by Andrew Parnell in Maynooth in Ireland, which has some amount of users, especially in the C-level community. And then I'm really happy to see Bacon, which since 2011 has become very popular and has now many more citations per year than, for example, CLAM. And I'm really happy to see that, because I think Bacon and its Bayesian companions does a much better job at estimating uncertainties. Yeah. Okay. Right. So, but what is Bayes? Because I was in the year 2000 or so, I attended a talk, and I was actually giving a talk, and then someone said, "Why don't you use Bayesian stats?" And I was like, "I have no idea what that is. Couldn't care less." No. But then later on, I saw the light, and indeed, it's I think a good idea. So when most people think of statistics, it's the classical frequentist statistics, and much of that was developed actually by one person, Sir Ronald Fisher. He Well, he was part of a larger group, but he wrote 2 handbooks that became very, very popular among research statisticians in labs and elsewhere. He introduced, say, classical statistics when we think of, say, 5% significance level or ANOVA. That's the type of statistics that he developed. And that's really, yeah, it becomes synonymous with statistics. I myself, however, never ever use it. So one reason perhaps why it becomes so popular is that it was actually fast and easy to calculate. You had a handbook, you can just get some formula, and then you can get your outcome of your statistical test. And they're globally very, very popular. But some of those tests were actually simply meant as exploratory analysis, just to see, okay, what is in my data, and never really to say whether or not things are significant and should be trusted. Yeah. He also has a bit of a doubtful history with his political opinions about Nazis and all. So if you are if you want to think about that, perhaps you should not look too much to Ronald Fisher, but go again more for Bayes. So Bayesian Stats was developed by quite a bit earlier than the classical statistics, in the 1700s, by Rev. Thomas Bayes. And in his lifetime, he published only 2 or 3 papers. Yeah, very low on the citation scale. He wrote, so he was mostly working on religion, but also a bit on mathematics. And he had an idea of, yeah, how could we take the context into account when we look at our new data? How do we marry new data with existing knowledge? He never actually published it because he died before he could publish it. So a friend of his published it as a thesis. And then that stayed as an obscure type of knowledge for hundreds of years, literally, because nothing could really be done with it, because it was just too complicated to actually put into practice. Yeah. So instead, classical statistics in the 1900s took over since the 1900s. Yeah. So classical statistics, we're asking here, did the sun just explode? It's nighttime, so we're not sure. Yeah. So here's a detector which just rolls 2 dice, and if they both come up with 6, it lies to us, and otherwise it tells the truth. So if you then ask the machine, has the sun exploded? And then it says, yes. Okay. So if you're a frequentist statistician, as most of us are educated, then you say, well, how likely is it that 2 sixes would have come up? Oh, that's 1/36. That's 0.027. So 2.7% chance of that being correct. Since that is below or under our alpha level, I conclude that the sun has exploded. That's just the frequentist approach. The Bayesian would say, I bet you $50 that it hasn't. Yeah, because they're looking not just at the data, but they take other information into account. Yeah, and betting is really a part of that. It's if the sun would have exploded, then £50 would be worthless anyway. So you can spend even 500 in your bet, because yeah, he can be quite confident of the sun not having exploded, given all the context that is there. Yeah. So classical frequentist stats tests whether an event or hypothesis occurs or not, and calculates the probability of an event if the experiment were to be repeated under the same conditions. On the other hand, Bayesian stats expresses everything in probabilities between 0 and 100%. And it is a way to combine new data with existing knowledge, existing data. So it is a way to update our understanding. So we have prior knowledge, and this understanding could be based on context and on expert opinion. Sounds all quite vague, but I hope it will become clearer later. Okay, so let's look a little bit at conditional probabilities, or probabilities anyway, and how they depend on the context. Okay, so what is the probability that I don't have a coin here, but imagine I had a coin, and what is the probability that if I have it, I have one here, that it lands on heads? Anyone? It's about 50% or so, I'm guessing, would be the answer, which is, yeah, most likely. It could fall perhaps on the side and then stand there, which is something that hardly ever happens. So we can ignore that possibility, and we give it a 50% chance. Yeah. Okay. What is the probability that I have over 20 pounds in my pocket? So how likely is that? Anyone, you can speak out. How much is 20 pounds more or less in dollars? No
30.
one? Sorry?
About $30.
30, yeah, So how likely is it that I have that amount of money in my pocket? So we need a context for there, right? We're at the end of the month, so my bank account could be quite empty, perhaps. I'm at home. I might be in my pajamas. I'm not. I might not be carrying cash because we're all going electronic mostly anyway. Yeah. So, and well, you might think, okay, how much does this guy earn? So there's all kinds of information, but we need to get an idea of the probability, right? What's the probability that it will rain tomorrow? Well, again, that depends on where you're asking, how to define rain. So again, depends on the context. Or even events that happened. Yeah. What's the probability that it rained yesterday in Bangor? Quite a rainy place, at least the Bangor that I'm aware of, but there might be quite a few more Bangors. The Bangor I'm thinking of is east of Belfast, which is a small one. There's also one elsewhere in the UK, and surely there's a few in the US. Yeah, so we need to know more. Or, for example, think of a couple that had 5 pregnancies, and all of those 5 were male. Now, what's the probability that their next child is female? So what do we think? A tenth?
50.
50. Yeah. So some people will say, oh, there's something going on, and perhaps there's some disease or something that's some factor which is causing all the males or all the babies to be males. But that's the other way of thinking. Is it, well, we already know from the context that about half of the children when they get born are male, half are female. So these 5 additional data points don't really add anything to our known half probability. Yeah. So it depends on what you think and of the information you have. All right. Okay. One more test, and then we might take a break. Yeah. So thinking again about context. Yeah. So how could Bayesian statistics be used to, for example, for COVID tests? Yeah. So this is taken from The Guardian here, and it's a really nice article. And they try to explain what Bayesian Stats does. So imagine a very accurate test for a rare disease. If you have a disease or don't have it, it will correctly say so 99% of the time. Yeah, so it's very accurate. in both false and non and true. Yeah. But the disease in question, I don't know which disease we're talking about, is very rare. And this is from April this year. Yeah. So the disease in question is very rare. So only one person every 10,000 people has it. So that's your prior probability. So we know the background rate of the disease in the population. Yeah. Okay. Now imagine that you use that test, that very accurate test, to test 1 million people. Yeah. So of the 1 million, there are 1 in 10,000, which is 100 people who will have the disease. Even without us knowing or testing for it, we will know that that's how many people will have the disease. And your test, the test correctly identifies 99% of those 100, so 99 of them. And then there's all the rest of the people who don't have the disease, and your test correctly identifies 99% of them again, so 989,901. And that means that despite that your test is telling the right answer in 99% of the cases, it has told 9,999 people that they have the disease when in fact they don't have the disease. Yeah, these are false positives. So if you get a positive result, there is your chance of actually having the disease is 99 or in on 10,098. So just under 1%. Yeah, that's if the disease is rare. If the disease was not so rare, if, for example, 1% of people had it, then you should interpret the results of your test in a totally different way. Because then you'd have many more false positives and about the same amount of true positives. And then if you would have a positive result of your test yourself, then it would be more than 50% likely to be true. Yeah. So it depends on the context. Is that more or less okay? As we will now take, I don't know, 8-minute break or 7-minute break, and we see get back at 10 past the hour. Is that okay?
That sounds good. And yeah, as you muse on Bayesian math, come up with questions that Martin can answer at the beginning of the next session. Okay, thanks. See you in a few minutes.
Oh, wait. Shall we get started again?
Yes, I think we
Yeah.
can do that. So Martin, there are a couple of questions in the chat, and then I have one from an earlier chat.
Okay.
But if you want to address the first one from Chris Conwell, if you can see that.
Yeah, the PDFs
that
for
would
each
be-
calibration point in the Bayesian age-step framework shown in your samples are presumably based on analytical uncertainty of radiocarbon measurement. Can we still use a Bayesian approach if our points are based on other types of dates, and in this case, biostratigraphy? So the position of biozone boundaries. Yes, and it has been used, and there's a few cases where older types of sediments have been age modeled using Bayesian statistics. There's a few papers in geology that I'm aware of, where Bcron has been used. And there's also Bacon has been used for a site related to the Deccan traps 65 million years ago, 66. So you're not restricted to using radiocarbon dates. It's simply, we use them most because that's what we're used to. But anything that has uncertainty, an age estimate and some uncertainty should be available for use in our age depth modeling software. And the next question is actually quite similar. So what if you have luminescence dates or a magnetic reversal or tephra dates? The one thing that has to be said is that we do need an estimate of the uncertainty. Yeah, so you do need to be able to tell me, okay, I've got this biostratigraphy zone and we know its age is 20 million plus or minus something. We need to know that plus or minus. Same for luminescence dating, we need to know the uncertainty, same for the magnetic reversal. And for now, we have to assume that those are normally distributed, symmetrically distributed errors. That's the only limitation there. Okay.
And Martin, the third one was earlier when you were talking about hiatuses, and you were using that hiatus at 470 centimeters as an example, but in real life, when would we be justified for assuming a hiatus at a certain time? I mentioned lithostratigraphy, but I'd like your more broad.
Yeah, certainly. If you see it in your core, that is a very good. Yeah, so if you have additional information for there being a hiatus, if it's based on stratigraphy, and then if you can pinpoint quite well, then based on stratigraphical indications where your hiatus should be, then that's the best way. Sometimes it's actually based on radiocarbon dates. So you have quite a homogeneous stratigraphy, but then your dates show a jump. And then, yeah, you'll have to decide on what is the best depth there. So that's not a parameter that we are currently estimating ourselves. That's what the user has to provide as an option. Yeah.
And Lisa and I actually have a very strongly hiatus-driven lakes in our work in the Bahamas. Any other questions before we let Martin take off on Bacon? Okay, we'll try to be conscious of taking another quick pause in about half an hour, but otherwise, Martin, take it away.
Okay. So yes, I do have more than 20 pounds in my pockets, in my wallet, and these are really weird pounds. I don't know if you've ever seen pounds, but these are the weirdest. They're Northern Irish pounds. They're almost worthless outside of Northern Ireland. No one wants them. Right. Let's share a screen. Can you see the screen? Yeah? Hope so. Okay, so Bayesian statistics, let's look a little bit more at that, and then we'll leave that aside and go to actually the models. But what Bayes proposed is to have that your posterior knowledge of your data and your prior, so the knowledge you have, how we update that the posterior is proportional to the likelihood of the data given the prior times the probability of the prior, which sounds quite perhaps difficult to envisage, but that's the basic idea behind Bayesian statistics. And as I said, for centuries, nothing could be done with this because it was simply too difficult to calculate these factors. No? Oh, sorry. Of course, it's very difficult to calculate it analytically, so not much was done with it. And it only became popular in the 1990s when Oxcal came out and when lots of Bayesian approaches came out, because that's the time around when the Titanic movie came out, when computers became fast enough, personal computers became fast enough, and also algorithms became stable enough and useful enough to actually start approaching the Bayesian question, but not in an analytical way, but through taking many samples. Yeah. So we're using MCMC, a Markov chain Monte Carlo. Monte Carlo is simply you randomly sample a value from a distribution, could be a normal distribution, for example, or a calibrated distribution, and you do that thousands of times and calculate your models. But what's done here is that it's not, you still sample randomly, but you have a degree of, like, you have a chain of iterations where the next chain will depend on the previous chain, on the previous iteration. So we change our parameters one by one in a random way. And that, we will see later, is a way to combine our prior information with new data. It's a way for our model to learn from the data. So what it does, it simply, the model simply produces some initial values. If you have 5 values that you want estimates for, you simply produce 5 values, whatever the values are. And they should fit the data more or less. It doesn't really need to fit it perfectly. And they should also obey any prior information that we have. For example, we might know that our the values should be ordered, should be increasing in a monotonous way. Yeah? So they should fit the data more or less, and they should obey the prior information. They should not, they should obey the prior. Then that initial set of 5 values, then we randomly choose one of those values, for example, the second one, and we change it by a tiny bit. Yeah, you randomly change that original value by a tiny little bit. And then you either accept this new iteration as a new model, a new Santa Claus with a child on his lap, and you accept it if the new value enhances the fit of the total fit of the data. We'll come to that. And if it doesn't enhance the fit, it still has a likelihood, a probability of being accepted, that iteration. And that is that process we repeat then millions of times. Yeah. And after having done that millions of times, you have then a Markov chain Monte Carlo values for all your 5 parameters. For each of the parameters, we'll have 1 million estimates, and we thin the estimates, so we get rid of some dependence between iterations, and that will then give us say not an analytical but an approximation of the true values of the parameters that we're after. Yeah. So for example, if you have just a normal distribution here, and in red, I'm sampling, just randomly sampling values from the random distribution, but each time I either accept the iteration or not. And if my fit for the next iteration becomes better, then it will be accepted. And if it's lower, it will be less likely to be accepted. That simple approach, using one parameter, will in the end, this gray distribution more or less fits the true distribution, which is the one in green here. Yeah, so this process of learning from your data through a Markov chain Monte Carlo works quite well. Yeah, so in the end, after a few thousand iterations, we see that what has been sampled is more or less, but not exactly, what the original data is. Okay. That also brings us to, these are based on random numbers. So each time you run an age model, a Bayesian age model, it will be different because we start with different starting numbers. And so each time you run something, it will be slightly different from the rest, from other times you tried it. Okay. Now, we can also use a Gaba distribution, and I really like gamma distributions. I prefer them over normal distributions because gamma, the values are always positive, always larger than 0. And that's really handy for example, estimating or modeling, simulating accumulation rates, because we can't have accumulation going backwards in time. It should always be forward in time. And therefore we use the gamma distribution for our accumulation rates to, that they should obey this gamma distribution. So we have them always positive, always increasing with time. This has 2 parameters, just like the normal distribution, a mean and a shape, which is how peaked that distribution is. And again, if we use the same approach to MCMC, you can then get, after a few thousand iterations, you get a reasonable approximation of the underlying distribution. Yeah. So there's many different types of gamma distributions that you can set. So depending on the value of the 2 parameters, you can have a gamma distribution that looks almost like an exponential one, or you can have a very peaked distribution with a very high value for shape, or it can be quite broad and accepting many different ones. And that will then set how, your prior information on what values your distribution could take. Okay. There's also the beta or beta distribution, which again, it's quite a useful one. And in this one, it's always larger than 0, but also always the maximum value it can take is 1. So it's between 0 and 1. And that's helpful to model, for example, memory or something which can be between 0 and 1. Yeah. Okay. So let's now finally go to age models to see how this could ever make sense for age models. Yeah. So imagine that we have a site, a sequence, an archaeological sequence perhaps, and we radiocarbon dated 5 levels. We don't really know their depths. We know that they should be in chronological order. So the further down, the date should be older than higher up. That's all we know and all we want to model. Okay. So we model them to be in chronological order. So what we do, we sample some initial 5 ballpark values for years for these 5 radiocarbon dates, which is simply something, anything. Yeah, but they should be in chronological order. That, of course, that's what we want them to be. And if they're not, then that is not accepted. Yeah. So we've got 5 initial values. And then again, we go, well, first we calculate how well they fit the calibrated radiocarbon dates. And we'll come to how we do that. And then again, randomly, we choose one of the parameters and we change that one parameter by a tiny little bit. Yeah. And then again, we check first that the values remain in chronological order, not that there's necessarily, say, a reversal. We don't want reversals. If there's any reversals, we will not accept them. And if the fit with that new value, for that new proposed iteration, if the fit has been enhanced, we accept it as the new iteration. And if it's the same or slightly worse the fit, then we possibly accept it and we possibly do not accept it. And that again, we repeat millions of times. For example, for Bacon, we can easily do that 6 million or 20 million times. And at the end, we just remove burn in, so the initial iterations, and also, we only store every 50 or 100 or 500 iterations to get rid of some memory effect between the iterations. Okay. So here we see that in action, we've got 5 dates, which we know are in order, where date 5 is the oldest, then date 4, then date 3, 2, and 1. But in this case, this blue date here happens to be older than the other dates, but our model says, no, it should be in chronological order. So it just starts modeling values outside of the calibrated distribution. And we come up then with the gray bits here, which are simply the new modeled dates, modeled ages based on the 5 dates and the enforced chronological ordering. Yeah. We start off with really bad fits, but the process of like comparing the new iteration with the previous one and accepting it if the fit is better, and possibly accepting it if the fit is worse, that's a learning process. Yeah. So we over time we learn. Yeah. So through this process of MCMC iterations, we use the data and combine it with our prior information. And so in that way, we learn from the data and update our information. Yeah. Now, in this case, we're only running 2,000 iterations here. So there's very few iterations, and we need many, many more in order to get a good, reasonable estimate of the values involved. And also, of course, there's a lot of memory. There's so many iterations where there's actually no change happening. Of course, the proposed iteration doesn't really increase the fit. So so many of these iterations will simply be quite repetitive and have a large memory. So later on we need to get rid of all those intermediate iterations and only accept and work with just a sample of all those iterations. I hope that makes sense. So in the end, you end up with say around 4,000 iterations, which have been thinned. So this memory process has been removed. So there's no structure. It's like white noise, more or less. That's what you want in your MCMC output. And then we've got our, in light gray, our original dates, and then in dark gray, our model dates for them to be in chronological order. Okay. If you want to play around with that, you can use this code here. So that's this new package called Coffee. And you can then simulate a stratigraphy with 5 dates. And then you can run that model of say with 10,000 iterations. We won't do that here now because it takes quite a bit of time. And especially if you want to have at least say 3,000 remaining iterations, you need to run this thing for a few million or perhaps a few tens of millions times of iterations. So that will take, well, a few minutes or perhaps up to an hour or so of running. So we won't do that here. But you're more than welcome to start using this and report any feedback to me. Okay. But that's not the only model we can use. We can also think of other models. For example, if you have a tree where the tree has yearly rings, which can be counted in a very precise and accurate way. And then you have radiocarbon dated your tree at gaps of exactly 10 years, for example. Yeah? And then you've got loads of money and you've got loads of dates. And so in this case, we've got many rings that were radiocarbon dated. And then we can use that information on the spacing between the radiocarbon dates to get a very good handle on. So that's our prior information. And by combining this prior information on the exactly known spacing in time between dates, we can combine that then with our radiocarbon dates and end up with what originally in blue was the original calibrated years that become then very precise once you get your age modeled ages. Yeah. All right. So stratigraphical order of dates is something that we already discussed. It's a very easy to defend approach or model or assumption in many lake records or other sites. And it's simply the process of running many age estimates for your ages, and then only accepting those that are in chronological order. And if there's any reversal, you take those out. You don't want the reversals. And if you do that many times, you can get models that are more precise than the individual calibrated ages, and they will also kick out outlying dates. So that's really useful. Right. I'll just go over this. Another model that can be used would be, for example, straight accumulation. Yeah, so our site is accumulating linearly over time, but we don't know exactly how fast. So we have two parameters, the slope and where it fits. And we can simply change A and B, and that will then change our H-step model, and that will then change the fit of our dates to the calibration curve. So that's, yeah, assuming, that's a very big assumption, but assuming a entirely linear accumulation, which is perhaps not a very reliable thing to assume. Yeah. So what we are doing now for Bacon is that we have a linear model, but piecewise linear model. So if we have a core of a few meters length, we divide it into sections. Each of those sections is, well, in this case now 50 centimeters long, so a very wide, very thick section. Okay, but imagine if we do that. We have a 2 meter core, and we divide it into 50 centimeters sections, which are 4 50 centimeter sections. And so we have a model which is simply a piecewise linear model with 4 sections. Yeah. We assume linear accumulation within each section, and the value of that linear accumulation is constrained by a gamma distribution. And then we also have 4 dates, and then for each iteration, as we saw before, we calculate the fit, and the fit is simply the product of the likelihood of the priors times the likelihood of the dates. And I hope that works. Yeah. Oh, here's Amora again. Okay. So here we're combining our dates with prior information on our accumulation rate. And by doing so, the model will try to combine each time the prior information with the data. And it just chooses random values all the time, but accepts those random values more. They're more likely to be accepted if the fit is better. Yeah. So that's the way we learn. Our model learns. So over time, our fit will get better and better, and we'll start hitting this date here as well. Yeah. Even though the elbow or the slope that is modeled in order to fit that date is actually quite an unlikely slope given the prior information. So here we have combined our prior information with the data to come up with a model which has combined both the data and the prior information, and that is then our model. Okay, right. So that's more or less what's behind Bacon, although what it does, it doesn't use just 4 sections, but many more sections, and the sections are only 5 centimeter wide. So you have your core, you divide it into, by default, 5 centimeter sections, and model linear accumulation rate for each section. And the accumulation rate is constrained by the prior of the accumulation rate, and that's actually years per centimeter, not centimeter per years. Sorry about that. And it's not only that, it's also the memory. So how fast, how much can accumulation rate change from one depth to the other? And that's the memory. Yeah, and this memory can be very close to 1, and then there's a very large memory. So then the accumulation rate at one depth will tell what the accumulation rate at the next depth will be. So your core is almost accumulating in a very straight line. Or it can be 0, so very close to 0, where there's hardly any memory. So whatever happens further down a core or up a core doesn't affect what happens elsewhere. So this is the prior information we set on the accumulation rate and its variability or memory. And that then sets the model. Okay. And many people will cut out the upper panels and only show the lower panels in your papers, but please don't, because I really want to see how well your prior information and your posterior information fit, what settings you've been using, and how well the fit is, how well the MCMC run went. Okay. So we can use those, like those grayscale H-step graphs that we see here. We don't just use then the mean or the median, the red line. We can use the whole family of H models. Yeah, the whole grayscale of H models. That's important. So not just reduce all the uncertainty to one curve, but use all the curves together. And we can then use our H-step model to also plot our proxies as a grayscale. So on, with taking into account the uncertainty we have about the very H values of our proxy features. Okay. Yeah, I think we're running a bit out of time. I could perhaps skip this because Amy has already put in the chat the paper of comparing Bayesian and classical H-step models. And I think, yeah, we're running out of time, so I won't really go into that. If you want to know more, we can perhaps discuss that next week. But what it does is compare classical and Bayesian H-step models. And classical ones are fast; they run within a second or so or less, and they seem to be very nice and precise. And that's what we would want to have, like high precision, and even or especially at low dating densities. On the other hand, Bayesian models are slower. They take minutes to run, or sometimes hours. And they show larger uncertainties, especially if you have few dates. So that seems to be a bad thing to do. Yeah. But the precision of classical models is illusionary. That's what the paper showed through simulations. Even if you have a very precise CLAM model, it might be very wrong. It might be very far away from the truth. On the other hand, Bayesian models are more pessimistic, but they actually mean that they're quite accurate. The estimates of the uncertainty provided by Bacon and Bicron and Oxhell are actually quite realistic estimates of uncertainty. Sorry. And with classical models, we already have seen that more dates, added dates, doesn't really increase the precision of the model. Whereas for Bayesian models, we learn. So with each additional date, we will start to learn more about our core, about our H model. Classical models, for them, outliers will be disasters. But Bayesian models handle outliers really well, because there's several processes in the H models that model how a date could be outlying, and with that, it's quite robust to up to 50% outliers or so. So in the end, well, classical models are popular, but we see that they're becoming less popular now, and that's probably for a good reason, because they're not really well suited to their tasks, whereas Bacon and Bicron and Oxhell really, they outshine classical approaches, not just for high data density sites, high density data sites, or for many dates, but especially if you have few dates, then your model and your uncertainty estimates become very, very important. So use your Bayesian model also if you have only few dates. So in the end, Bacon really seems to win. Yeah, it deals much better with outliers, reliable uncertainty estimates, and robust, whereas classical models, yeah, they're just sad. Just don't use them. Okay, good. So we've talked about Bacon. Oxcal does something similar. It is like akin to droplets in a bucket, and that's how our site accumulates. And the size of the droplets, that's the K value. And you can set that to small values or large values, or you can actually leave that empty and let Oxcal come up with the correct value. And it does a good job in dealing with outliers and so. Then we've got bcrom, which is it estimates jumps in time and in depth, and the jumps are random. The length of jumps is random, and in that way it produces a model which looks a bit like to me like a string of sausages. I have nothing against sausages; goes well with bacon, but it's I think they're perhaps the uncertainty is sometimes a bit overestimated. Then there's also bpeach, which we'll not really discuss because it has been updated to Bacon. And as we said, Bacon divides a core into sections, models each individual section as a linear accumulation rate, and the accumulation rate is constrained by prior information, and so is its variability. Okay, right. And after making a model, you can then actually, then things become interesting. You can start combining different models and seeing how the timing of events compares between different cores. And that's something that we'll, if you want to, we can have a look at, especially next week. All right. Okay, are there any questions for so far? That's the theory. That took much longer than I had hoped. Any questions or remarks? Just going to stop sharing for a while.
I have a question that I put in the chat. Can everybody hear me okay?
Yep.
Okay, so I had a question that on our Bacon, the graphs at the top, there are the green lines and then there are the gray lines which reflect your modeled results. Should those be as close as possible to one another, or could there be variability in those? I guess, how do we know when we've done things well?
So it's a good question, and it's a bit hard to answer. If the posterior, so the gray one is much more peaked than the prior distribution, the green one, then we have learned something. Yeah. So then by combining our prior information and our data, the model has learned that the memory is of a certain value. We have learned more now about that. Yeah. So if you see that originally our green prior distribution is less peaked than your posterior distribution, that's actually fine. Then we have learned. In many cases, they will be quite similar. So there will be a bit of a change perhaps, but there will be quite like overlapping. And then that means that our prior information, which is, I think the default is 20 years per centimeter, or is it 10? I always forget. So that seems to be a reasonable prior for many lakes.
It's 20.
So in that case, we haven't learned much. And so you don't want to have like an exact overlap. It doesn't, well, as long as they don't really entirely disagree. Yeah. If they entirely disagree, then the prior information is not correct for your site in question. And then you could perhaps adapt your prior information. But that would also mean then it's not really prior information anymore, because you've then already looked at the data. Yeah. And the same for the memory. So both the memory and the accumulation rate priors are the priors are set quite wide, so they could assume many different values. So they're not very prescriptive. In some cases, you might want to have that you have lots of information on the accumulation rate, for example, in a site. Then you could set the prior to be much more peaked and restrictive, and then your model will take that into account. Okay.
And I think that Nancy's question was pretty much the same thing about the prior and posteriors matching. And Martin, I know we only have about 15 minutes left, but I think if you wanted to go over by a few minutes since we're recording, that would be okay. So
Yeah,
just so folks are aware of that, we do have a recording. So hopefully we can, if Martin is able to stay with us, we can finish up everything that he has intended to cover today.
Okay, I'll try not to overrun by too much then. Shall we move on to the practical part? Is that okay? Okay.
Sorry, yes, that would be great.
Aha. So yeah, the default accumulation rate in Bacon was changed a few years ago based on Simon Goring doing an analysis of lots of lakes in North America. And then we changed, based on what was found there, we changed the default setting. And that same default setting was then also applied to Mars. So a deposit on Mars, its thickness was inferred from remote sensing data. And then that was combined with the prior knowledge of accumulation rates of lakes on Earth in order to come at an estimate of how long that lake had been active for on Mars. So there we have no data for Mars, and we're only using the prior information to get an estimate of how long the lake had been active for, how fast it accumulated. So that's the interesting case of having only prior information and no data to update our information, because we simply don't have the data.
And we did have one hand raised, David.
Oh, sorry.
Go ahead.
Yeah, I mean, this might be something you get to later, but will you speak about whether we should ever remove data from our data set based on, you know, our thoughts of whether it's a reworked piece of wood or that sort of thing, or whether we should always keep the data in?
I would prefer for you to keep them in, because I think it's more transparent. And in many cases, the Bayesian age models will deal quite well with outliers. So I think it would be more transparent and, well, reproducible to keep in your data. Unless you have a very clear reason that, okay, no, this actually is a wrong date, then you can take it out. But if in most cases, the age model will not really be offended too much by a bit of scatter. Okay.
Okay, thanks. That's good to hear. Yeah.
Yes. Am I still sharing my screen? I can't see. Yeah.
You are not, as far as I can see.
Oh, okay. Because I'm also, it's very slow here now, Zoom. Is it okay if I just leave the meeting and come back? Just me?
That should be, or what I've been doing to fix Zoom is just closing it, is just shutting it down. So you should be able to shut the window instead of actually going out and coming back in. Try shutting the window, and then it should reconnect you.
Okay, I'll try that.
Either way. Lisa and I will entertain you in the meantime.
Okay, so I'll come back soon. No, not working.
Any other questions that we might be able to answer?
Right. And especially if people have to go at 2, it'd be good to know if there's any sticky points. Yeah, that paper that you put in the chat, Amy, it was on neotoma, is a really interesting paper that people should.
Yeah, I will try to get the full citation in there. Yeah, Laura, do you have a question?
Do you know I guess maybe it's just in like the Bacon instructions, but is there somewhere we can find a good explanation of like what all the graphs mean? Because I'm still a little fuzzy on that, like at the top of the model, what all that, like how to interpret that.
Yeah, for sure. And I think that's one of the things that I've always had a little bit of trouble with. I think that part of the explanations that Martin went through just a few minutes ago helped me. But that's probably because I've read there's the Bacon paper from 2011, which I'll put the link to the chat in as well.
Yeah, that paper was written for a stats audience, and I am writing a paper that should explain more. Okay, what should we be looking for in the different outputs, and also some updates of how Bacon works. But there's so many other things. But yeah, I really would like to get that one sorted someday.
And is there anywhere currently, Martin, that someone could reference for explanation of how to interpret those graphs, even sort of to?
Not really that I'm aware of. There have been a few papers that have compared different Bayesian age models, but no, not that I'm aware of.
Okay.
But yeah, don't cut away those top panels. The MCMC of the top left is very important for people to see how that the model has been running well, and then the middle panel and the right panel tells you how well the prior and posterior information match and what the settings were. And I think that's also important for people to be able to reproduce the same output. Okay,
Yep.
yeah,
And there
when
is,
it gets published, yeah, it would be great. That would be still a while to go before that new paper would get published.
Yep.
Okay. Right. So
and remember that there are a number of tutorials. I think that Martin will link to those, or link to those at the bottom of the of that GitHub page, where all the code for the course is. So there are, if you're worried about missing out on some of the hands-on stuff, there are a number of things that you'll be able to take a look at as well.
Yeah. Okay. Now I think now I'm actually logging out and back in again actually worked quite well, it seems.
Great.
For me at least. Can you see my screen? Yeah.
Yep.
Good. Okay. So you know, I will not go through CLAM now because we've already done that and we're running out of time. So I will not go there. Okay, this is not my cat. This is Pixel, one of my favorite Facebook cats. All right, so if you haven't installed Bacon yet, it's called RBacon when it's in R. So which I hope you've all done. And you only need to do that once, then it's installed in your computer. But sometimes if there's updates, you might want to run this command again. And once you've done that, then you can load the code using require RBacon or library RBacon, doesn't really matter. And then you run Bacon by the Bacon command, capital B, Bacon. The first time it runs, it will ask you whether it's okay to produce a folder called Bacon runs, and it will put that in the folder where R is working at the moment. And if you're okay with that, you simply press enter or type Y and enter. And so in my case, for example, it will be put in, when I was working on my Mac, it was on the users, Martin, desktop, and then there's this umbrella folder, Bacon runs, and within that folder there will be more folders for the different cores. And the default core here is MSB2K, and that's the core that comes with Bacon. And it then asks, shall we run it with 20 sections? And you say yes if you agree to that. And if you do that, you end up with a model like this. Yeah, where in the main panel you've got in blue the calibrated distributions, and in gray the age model, and in red the median or mean age model. And then on the top left you've got your MCMC iterations, which should show white noise but no like major structure. And then in green you've got your accumulation rate prior and the posterior in gray, and the memory is in green and in gray. What's underlying in the model is simply the accumulation rates, that the sedimentation times is what the model works with. And you can then also plot them against the accumulation rates as grayscale against depth of the core or against age. Yeah. Right. If you want to run Bayesian with fewer sections, that it's the second option. So you can say that there should be, instead of 5 centimeter sections, there should be thicker, 30 centimeters. And Bayesian will complain. It will say, no, don't do that, because it's a bad idea, because there will be too few parameters and the model will become very elbowy. But you say, no, we do that anyway. So then you can run a model with much thicker sections. Not a good idea, but you can do that. You can also imply all kinds of hiatuses. So you can say that there's a hiatus at 23 centimeters depth, for example. Or if you have multiple hiatuses, you can combine multiple values by typing C brackets and then your multiple hiatus values separated by commas and then close bracket. There's also a thing called a slump, or which perhaps is a badly named thing for say what do you call it, like a turbidite, or something which accumulated instantly or almost instantly in your core. For example, a tephra layer which was deposited instantly in an otherwise constantly accumulating core. So you can excise those depths from the age model and put them back later in, so you can get your model with slumps in there. If you want to see all Bayesian's options, you simply type question mark and then Bayesian, and that will tell you all the options and some explanation of what they do and how they can be changed. You're also certainly welcome to adapt the priors for the memory and for the accumulation rate. And you can do that by typing, for example, that accumulation.mean. So the mean of the prior accumulation rate, which by default is, I think it's 10 or it's 20. You can set it to something else if you have information for that. Yeah. Okay, then the output of the Bayesian model is simply lots and lots and lots and lots of accumulation rates for each of those sections. And so for each of sections, you will have an accumulation rate estimate, and you will have thousands of estimates for each of those parameters. And that's an output file which you normally wouldn't have to look at. It's simply something that is stored in the course folder, and that will then later be used by Bayesian to calculate age models for any depth. Yeah. So normally don't have to worry about it. You can also use Bayesian to run another core. For example, the other core that comes with it is RLGH3, which is a lower density dated core, and it has a few outliers or sections where some dates seem to suggest something else than the other dates. So that's quite interesting to try to model. So you can model that, probably not now because you have little time, but by typing Bayesian and then use as the first option, and that's the core name, and you can change that by RLGH3. And all core names have to be quoted. Yeah. Okay. What Bayesian will then do is will look for a folder in the Bayesian runs umbrella folder. It will look for a folder RLGH3, and within that folder, it expects to find a CSV file, a comma separated values file. with the exact same base name as well as the folder name. And it will then read that file and expect it to find the dates in that file, read the file, and then produce the age model. And so that's the approach Bayesian uses. So you have to be quite particular in getting the naming exactly right. Otherwise, Bayesian will not find the ages and no output will be given. All right. So the format of those files, if you open a CSV file, a Bayesian CSV file, for example, the one of MSP2K, it will have 4 or 5 columns. And we'll have a header. So the first line, the first row gives the names of the columns. And the first column is simply a lab ID, just any name, doesn't really matter too much. Then the second column is the age, that can be a radiocarbon age or a calendar age. If it's a calendar age, it should be in CalBP, not in AD or BC. Then the third column is the error, which should always be larger than 0. Then the fourth column, which could be the last column, is depth. This is the midpoint of the dated depth. And what I would suggest you do in all cases is you add another column called CC, the fifth column, where you put a 0 for any date which doesn't require calibration, which is already on the CalBP scale. Yeah. For example, if your service age, if you know that you took your core in 1985, so in 35 CalBP, then you can add that as -35 plus or minus 10. So you have to give some sort of an estimate or a guesstimate in this case of what the uncertainty is there. And that is the depth, 0 centimeters. And the CC here, that's the 0, which means it's already in CalBP. We don't need to calibrate it. If we have IntCal 20 dates, so terrestrial Northern Hemisphere dates, then you can you place a 1 here, that's for IntCal 20. If there are marine dates, you put a 2 there. And if there are Southern Hemisphere dates, it's a 3. And if you have your own calibration curve, for example, if you've made a default calibration curve with a different type of smoothing, then you can use it as CC equals 4, and then you have to provide that calibration curve 4, which is like for tailor-made calibration curves. Okay. Now, I would always recommend opening the file as well in a plain text editor in order just to see that everything looks all right. Yeah, so just see if there's no weird many commas or weird things happening. And once it looks all fine, and if it's saved in the correct directory, so in the umbrella folder, Bayesian runs, and within Bayesian runs another folder named after your core, and then within that folder you have this CSV file with your core as a base name. Okay. Okay, so depths, Bayesian calculates by default the age estimates for any depths so every centimeter from the top depth to the bottom depth, and by default it does that every centimeter. But you can also do other things. You can set depth by to be something else, for example, every half a centimeter or every millimeter. Or you can also provide your own depths. The commands are here. Or you can also provide a file, a plain text file. And that file should also be in the folder of your core and should end in depths.txt. And then you just type Bayesian and you give as one of the commands or one of the options that you have a depth file that you want Bayesian to run. Okay. As for post-run analysis, you often might run a core and then a few weeks later you want to go back to that core and you want to look at it again. You can do that by loading a previous run you type Bacon and then the name of the core, and then say that run equals false. And if Bacon then finds the correct information, it will load that into the memory. Then you have to just quickly plot the data again, plot the age model again, and then that should have, if everything goes all right, it should then have the previous run in the memory again, and then you can do all kinds of posterior analysis of the data. Okay, so you can plot your plots again. One plot that I find very interesting is to make a ghost plot or a grayscale plot of accumulation rate against depth, which we already saw before, but the command for that is acc_rate.depth.ghost. Or you can also plot it against calendar age, and that's acc_rate.age.ghost. Okay, perhaps a few more minutes. We don't want to over too much, but say producing an age model, that's one step, but things become interesting once you actually have your age model and then want to interpret it and query it. And R is really helpful there, because your age model output will be in your R's memory, and you can start asking questions. Yeah, you can, for example, ask Bacon to draw a histogram of 20 centimeters depth, bacon.hist 20. There you can get this output. So it gives you the distribution of the ages around 20 centimeters depth, and it gives you as well a 95% range, for example, and a mean and a median. So that's helpful to look at individual depths and their ages. You can also ask for all the iterations and give me for all those iterations, give me the age of all those iterations for 100 centimeters depth. That's another command. That's bacon.age.d depth for 100 centimeters depth, for example. You can put that in a variable, and then you can get that variable, and you can play around with it. You can ask for what's the mean of that age, for example. You can query that variable in R. And if you do that for multiple variables, you can then start asking what's the age at 100 centimeters depth, what's the age at 50 centimeters depth, and what's the difference between the two? How much time has passed between 100 centimeters depth and 50 centimeters depth? And then you can also plot that or make a histogram of that. Yeah, so that's where R is really useful, that after the run, you can really get to grips with, okay, what does this model tell me about my proxies and about my core? I think that's, oh yeah, of course, I should also show that once you've produced your age model, the temptation might be then to go to the file and extract the mean age model, and then use that to plot all our proxies or our pollen or our isotopes against that one mean age stat model. But I would really recommend not doing that, because that would reduce all the uncertainties we have to zero. Yeah, it would throw away all the uncertainties we have, and instead we can use this grayscale model, the grayscale chronology of our proxies. We can plot our proxies against a time in grayscale as well, which unfortunately not many people are doing, but I think it's a good visualization of the uncertainty we have. I think that's me now, and I think what we do next session is we look at your own cores, and perhaps if there might probably be quite a few questions about Bacon. We look at that, and then we also look at Plum. Are there any questions now? I'm sorry for the delay, or anything that should be looking at now? Oh, there's the PowerPoint on session 2B page is missing a couple of slides. Okay, I will update that. Sorry about that.
And I know Martin ran through the sort of tutorial part fairly quickly. And there are probably some important things in there. I would, for all of you in the course, especially to catch up, to be in the right place for next time, I would say be sure to go through all of those Bayesian commands that are listed in there, that are in the code for today, just to run a few age depth models and see kind of how it works to play around with it.
I think that's a really good idea. And we could perhaps also start off next week doing those commands and seeing what the output is like, and work through it that way before we go to individual cores and to Plum, perhaps.
And what do you want them to do if they don't necessarily have a data set? just use it.
I think
Excuse me.
what people could do, they could offer to share their screen with specific outputs, and we can go through different models with few dates and with many dates and with weird things happening. That would, I think, always be a good learning experience.
And I can share a couple of published data sets too. One that is all radiocarbon, and one that has some tephra dates and lead-210 in there as well, in case people want to play with a few different things.
Yeah.
And if we'll get a survey out, but also let me know if you feel free to email me if you are lost or need clarification on various points, myself and Martin. But we can, you can ask questions at the beginning of the course next time as well, if you run a little bit of Bayesian in between now and then.
Yeah, and will there also be a survey?
Yes.
Yeah. So if
Yeah,
you
possibly the
need to
same
fill in
one.
survey as well.
Yep.
Okay. Any other things we should cover now? Okay, so what I'll do now is I'll update the 2B PowerPoint so that all the slides are in there. And Amy, will you send the recording so I can put it onto YouTube? So then
Yes. Oh, right. That's the other thing I was going to say is Martin is kind enough to have uploaded the recordings to YouTube. So they're linked on the page from session 1. And then the ones from today will be linked on the session 2A page, I guess. And so that's where the links will be. So we can send that out again. But yes, I'll download those and send them to you.
And sorry that I was a bit slow at the Bayesian part. It's just I get totally excited about all that, and then I forget about time.
We can see where your true heart lies.
Oh, great. Okay, so
Okay.
yeah, next week, we'll look a little bit more at Bayesian again, keep it to get it running. Look at some case studies, and then we go on to Plum, and perhaps if we're lucky, get some case studies of that as well.
Cool. Okay, thanks so much,
Excellent.
Martin and Lisa, and thank you, everybody. And we'll see you next week. Be in touch. Let us know where your sticking points are. I'll send you the survey. Thanks.
My stick insects are there, but you said sticking points, no? Stick insects. Well, anyway.
Really?
Yeah.
Cool. Thanks.
All right. Hi.
Okay, we'll
Thank you
have to
very
meet
much.
them next time as well.
Yeah. They're a bit boring, but all right. Okay.